Hello everyone, I am Charanjit here. Welcome to the class. I hope you are fine at your home. In previous video, we have done the representation of fixed point numbers. Now we are going to start the next representation, that is the representation of floating point numbers. There is no fixed position of decimal point, and decimal point keeps changing its position. Yes, example of floating point numbers. All fractional numbers are floating point numbers. For example, 1.110101. These all are the examples of floating point numbers. Here the position is not fixed. It changes according to the number. Next is normal scientific notation. By using this notation, floating number is divided into two parts, mantissa part and exponent. This floating number is divided into two parts. This part is called mantissa and this part, that is exponent part. Same in the second example. This number is mantissa part and this is the exponent part. How we obtain it? See here. There is no decimal point, so it means decimal point is at the end by default. So when we move this decimal point to the left, then the number of digits that it changes becomes the par. Yes, here we move the decimal point 5 positions, 1, 2, 3, 4, 5 to the left. So par is 5, that is the exponent part. See here, there is a decimal point and I want to move this decimal point to the right on this position after the two digits. So I move and there is a exponent part that is in the form of negative form. Next, addition of floating point numbers. How we can add two floating point numbers? If we want to add the two floating point numbers, then first step is write both the numbers in the same notation. We have to write the both numbers in normal scientific notation. Second, make sure both the exponents of both numbers should be same. If the exponent of both numbers are different, then shift the decimal point of number that has smaller exponent to the left. The number which has smaller exponent, we have to adjust that number by shifting the decimal point to the left side. So third step, perform the addition, and fourth step, if more than one digits before the decimal point is there, then we have to adjust that digits. Make sure there is only one digit before the decimal point. Here let's take an example. So I want to add this number with this number. Both the numbers are in the same notation. These both are in the scientific notation form. So now second step, make sure these exponents are same. No, exponents are different. So adjust the smaller exponent. How we can adjust? Yes, to move the decimal point to the left. Yes, like this. The exponent becomes 3. When we want to move the decimal point one digit to the left, then exponent par is increased by 1, like this. So both the numbers have same exponent. Now we can add these numbers. Yes, leave the exponent part as it is, write the exponent part as it is, and add the mantissa part. 101, 011, 110 and 1 carry, 111. 3 ones are there, so sum is also 1 and carry is also 1. 110 and 1 is carry. Yes, here see students, before the decimal point there are two digits. We have to adjust these digits. So for that I move the decimal point to the left side like this. When we move the decimal point to the left, then exponent par is increased by 1. So this is our answer. Next operation is subtraction. How we perform the subtraction on floating numbers? Firstly, make sure both the numbers are normalized. Both should be in the scientific notation. So second, make sure the exponents are same. If the exponents are different, then we have to adjust the smaller exponent to become the same exponents. So third step is take the ones complement of subtrahend, then add both the numbers. See here, I am taking this example. I want to subtract this number from this. Here exponents are different, so make sure I am adjusting the exponent 2 to 3 by moving this decimal point to the left side. See students, and total 8 digits, so last 0 is skipped. Yes, I discard it. Then this is a ones complement, so add ones complement with this number to perform the subtraction. So when I want to add this mantissa part, there is a 1 carry after the addition. So in ones complement, if there is a carry after addition, then this carry is added to the least significant bit. Remember students, we have done in the last video ones complement subtraction. So we have to add this carry to the least significant bit. So this is the result. Here before the decimal point only 1 digits. So no need to adjust the decimal point. This is our final answer. Advantages of floating point numbers. First disadvantage is when number is large, its precision will be less. And second is a smaller number with large precision cannot be represented in the memory. In memory we cannot able to represent the number with large precision. Okay, accuracy depends upon the precision. The number which has higher precision is more accurate than the lower precision numbers. And floating point operations carries always rounding off. If there is a minor difference, then we round off that number, then that becomes 0. Now we are going to discuss about the BCD code. BCD stands for binary coded decimal code. As we know, computer understands only binary digits, binary code. The instructions given by us are converted into binary code, then computer can understand that code and perform some task. BCD is the binary coded decimal code that is one of the oldest code to get the instructions converted by the system. Yes, it is the binary code which it is used to express the decimal digit in the group of 4 bits. We need 4 bits to represent the decimal digit in BCD. And BCD is also called 8421 code. That is obtained by this. 2 is raised to power 0, 1, 2 raised to power 1, 2, 2 raised to power 2, 4, 2 raised to power 3, 8. Now this is the table for BCD code equivalent to the decimal digit, and here we can write 8421, and to represent the one number we write only 1 here and others are 0. To represent the 2 we have to write 1 in place of 2 and others are 0 and so on. This is the BCD code equivalent to the decimal digits, 0 to 9 digits. And after the 9, if there is 10, how we can represent the BCD code? We have to represent the code BCD different for 1 and different for 0. It treated 2 digits. 1 is different digit, 2 is different. For 0, the code is 000. And for 1 is 0001. So for 10 it represents the code like this. Same in case of 12. It write the code for 1 and 2. Then it becomes 12 in the BCD form. But in binary coding system, binary number 12 is represented by, yes, this is the 12 number. But in BCD, this is the 12 number. This is the difference, students. In BCD, after the 9, 10, 11, 12, 13, these digits are represented differently than the binary code. Students, to represent the decimal digits, we need the 4 digits only for BCD. But to represent the alphabets, we need 6 bits to represent the alphabets in BCD code. So for A, there is a code 110001. How to learn it? 1 to 9, again 1 to 9, again 1 to 9. You have to write like this. And here we have to write 1 1. That is the code for 3 for 9 times. Yes. Then 1 0 again for 9 times, and 0 1, this is for 8 times, and 0 0 0 for 10 times. In this table, A is represented by BCD code, that is 110001, and octal is 61 for equivalent A. How we can write text in BCD notation? So for T, what is the code? Look from the table, this. For E, write the code from table here. So this is the code for text. Next is ASCII code. What is ASCII? It's an American Standard Code for Information Interchange. Mostly in today's world, ASCII code is used. This code is popular in data communication and it is used to represent the data internally in the microcomputers. ASCII code is mostly used in now these days, and it is defined in two ways. Its first one is ASCII 7-bit code. So it represents 128 characters. How it is 120? 7 bits to 2 raised to power 7 is 128. Here not 27. It is 2 raised to power 7. Yes. So to represent the 128 characters, it needs 7-bit code. So that's why it is called ASCII 7-bit code. This is the table for ASCII 7-bit code. Yes. So here 0 to 9. After that A to Z alphabets are there. Second is ASCII 8, extended version of ASCII 7. It needs 8-bit for representing the number. So it allows 256 characters. So here it is not 28, it is 2 raised to power 8 equal to 256. It needs 8-bit for each character and it represents the 256 characters. This is the table for ASCII 8 code zone. Here 0 to 9 and A to Z characters are represented in ASCII 8 code. These codes are different from ASCII 7 because in ASCII 7, 7 bits are used to represent the character. Here 8 bits are used to represent the character. Yes, it's very easy. 101 is code for 5 and 000 is 0. So hexadecimal equivalent is 50. 51, 5, 1, 51, 5, 2, 52. So it's very easy to learn this code. Next is IISCI or IISCI code. Indian Script Code for Information Interchange. This code is developed in 1986 by the Department of Electronics, Government of India. ASCII code is very popular, and when character is typed, the internal system of computer immediately converts the character into its ASCII code. But ASCII code is not suitable for displaying and printing other Indian script, where different states have different languages. Standard keyboard is basically English typewriting machine. So when we type English alphabet, numerals, punctuation, then it is impossible to display the print Indian script. Like that has a different shapes, different characters, and with matras also at the top, bottom, and left and right of the character. So for that, IISCI code is generated by the Indian government in 1986. This code is famous because this code has Indian language letters with matra sign as well as with her. That is at the bottom of the each letter. Last is Unicode system. English language is widely used in the communication in the world. So in different parts of world, people speak different languages. But English plays a role of bridge between the different types of people. So in same case of computer deals with only binary digits. and whatever way the information is being given to it. However, main problem was to present the same context in different ways. So there should be a single encoding system. For this purpose, in California, 1991, Unicode system is developed. This Unicode is universal code that represents a number of characters that are more than the ASCII code. This system includes Devanagari, Bengali, Malayalam, Odia, Tamil, and many more languages from the world. Main objective of this system is to ensure that the same software website should serve the purpose of different languages irrespective of platform. So this allows the transfer of data through different systems without making any changes in the original data. So Unicode system is also used in Java language. Java language uses Unicode system instead of ASCII code. That's all, students. I hope you have cleared all the concepts. Thank you so much. Goodbye.